Good afternoon, everyone. Thank you for joining Mega Asia webinar. I'm Grace from Mega Hong Kong. Today, our topic is Railway Network Protection, presented by our relay experts from Mega India, Dr. Dinesh Babu. This is a recorded webinar. You are automatically muted to prevent any background noises. During the webinar, if you have any questions, please type into the question box, which you can see on the left of the screen, or you can press the Ask Question icon at the bottom control panel. We'll answer your questions at the Q&A session. At the end of the webinar, please help us to fill in the survey, which is on the right of the screen, or you can press the Take Survey icon at the bottom control panel. We'll be sending a protection testing guide to those completed the survey. Attendees will be able to download an attendance certificate after they have finished the webinar and completed the survey. The recording link of this webinar will be sent to you in 2 days' time after the webinar. So without further delay, let's start now. Thank you for joining us today.
Let me introduce you our today's presenter, Dr. K.N. Dinesh Babu. Dr. K.N. Dinesh Babu has a wide experience in the field of power system protection and has been working with leading organizations in the field such as GE, ABB for more than 15 years. He has wide expertise in the area of application, design, commissioning, and fault analysis with various IEDs, and also has a hands-on expertise on IEC 61850 with SAS implementation. He holds a doctorate in power system and has authored and published more than 20 papers in international conferences and journals such as CIGRE, IEEE, PACWorld, etc., all in the area of power system protection. Currently, he is working for Mega as application manager for power protection products and leads the application and design team for India and APAC.
Of Indian Railway. So the presentation is divided into 4 segments: importance, classification, testing requirements, and the role of smart grid. So currently, let us start with the importance of protection. Why we should focus on power system protection, how important it is. So let us see that. So that's in a different location, and what we are seeing is in a different generation plan. So that's the first part, the importance of protection system. So as you can see here, it's a self-explanatory topic. There is no much to discuss about it. We need to understand the area where we are working on. That is, when we say power system protection, it's a very, very important area. Security and how to protect the equipment, because we are talking about equipments which are very, very expensive. A locomotive, a transmission line, and even we are discussing about the lives of the people. So protecting it is very important, and hence we are going to see the ways by which we are going to do that. So let's see in a step-by-step manner. Power system protection principle. So the technology has been changing. A lot of updations and smart grid, new evaluations have come up. However, the protection fundamental never changes. Ohm's law, Kirchhoff's law, these are all basic principles. In the same way, the protection principle is these two lines. Whenever a fault occurs, the faulty portion of the power system should be disconnected. The healthy portion of the power system should not be disturbed. So these two principles are very important. Whatever innovations happens in power system protection, it's only based on these two principles. Maybe some latest technology which works more on communication, intelligent electronic device, how to record information. These things we are reading a lot in the latest technology. But the fundamental principle is whenever a fault occurs, these are the two things which we always go through. These two things are further challenged by bus configurations. In a substation, you will have various bus configurations. Some of the bus configurations are like this. Single bus, double bus, triple bus. So you have a single bus system. You have three types in the double bus system and one type in the triple bus system. Or maybe you can even call it as double main or single transfer, three main system, etc. So these bus configurations actually create a lot of challenges in implementing these two principles. And in fact, the bus arrangements itself is for this principle. So let us see that. Example, what is the need for this bus arrangement? This is an example of a single bus bar. You have one bay connected like this. This is a bus bar and another bay connected like this. This box represents the circuit breaker. The red means the breaker is closed and the green means the breaker is open. When a fault occurs in this location, which breaker should open? So should we open this breaker, bay 1 breaker, or should we open bay 2 breaker? So by looking at it, we say that it should open bay 2 breaker. But now we want to know why we are telling that. What is the reason for choosing this breaker and why not this breaker? So the answer lies in the principle that we discussed. Whichever breaker which we choose should be based on this principle. So here we have three parts, bay 1, bus 1 and bay 2, three areas. The fault occurred in this area. So this area is healthy, this area is healthy, and this area is faulty. Hence, the faulty portion alone should be disconnected. Healthy portion should not be disturbed. Both are satisfied. Hence, the second breaker is the right one. So this choice is actually based on the protection principle. Let's see another example. The fault occurs here. Which breaker we should trip? The first one, does it satisfy this principle? Yes, the faulty portion is bay 1 and the healthy portion is bus 1 and bay 2. It's not disturbed. Okay, you may feel that if you open this anyway, there is no current feeding in this bus. So how do we say that healthy portion is not disturbed? There may be several other lines connected to it. So in this example, we have considered only few. So in reality, it is not going to be like this. Several lines will be connected to this bus and several outgoing lines will be connected to this bus. And when a fault occurs here, only this will be disconnected. So the other lines will continue to feed either in forward or in reverse direction. So let's see another example. Fault occurs here. Bay 1 healthy, bus 1 having the fault. Bay 2 healthy. But which breaker we will trip? The answer is both. And we don't satisfy the principle. Because bay 1 and bay 2 is healthy, only bus 1 is faulty. Hence, we need to go for another arrangement. This is called as the double bus bar. So in double bus bar, you have an arrangement like this, that is bus 1, bus 2. You have two isolators connected to bus 1 and bus 2 like this. So this one is isolator, the diamond. And you have breakers 151 and 152 and 252. So the first one stands for the bay number 152, 252. 52 is the ANSI code for breaker. 89 is the ANSI code for isolator. AB represents the isolator connected to bus 1. A is isolator connected to bus 1. B is isolator connected to bus 2. So 189A means bay 1 ANSI code of isolator, that is 89, and A represents the bus 1 connection. So in this you can have 20, 30 or 40 bays. It will be the same thing repeated in that nomenclature. So let's follow the red line, how the current is feeding or transporting. It's like this. This is open, so it goes like this. Bus 1 is charged, it goes like this, and it goes like this. Same fault in bus 1 as we have seen in the earlier example. Now what happens? Can I open this 189A and 289A? We cannot open because it's an isolator. Isolator is an offline device. We can only open the breaker. Therefore, we have to trip the breaker. Still, we have disturbed. Okay, so now we can open this isolator, close this isolator, and then close the breaker. Now what happens? Bay 1 is healthy. Bay 2 is healthy. Bus 1 is faulty. Yes, we have isolated it and we have shifted to bus 2. Thus satisfying both the principles. It is for this reason that we need to have various bus arrangements. So we can see the need for double bus itself comes into picture because of this power system protection principle. Single bus cannot satisfy this principle, therefore we have moved to double bus. Now, why do you need triple bus? So that means there should be some drawback in the double bus. So the drawback is here. The second part, the healthy portion should not be disturbed. This is a question. Did we really do this? We can say the moment the fault occurred, just going back to the previous one. Yeah. The moment the fault occurred, we tripped the breaker. That means you disturbed the healthy part. Then after some time delay, we switched and we brought back this bay 1 and bay 2. So that means there is going to be an interruption. That interruption is going to be for a long time because isolators typically take around 15 to 20 seconds to operate. So let's assume it's 30 seconds for one isolator to operate. That means for two isolators, it's 1 minute. So for one bay, you take 1 minute. So in a 40 bay substation, if you are operating all the isolators, you are going to take 40 minutes to do this. So roughly 40 minutes supply interruption. So though in this example, we have seen it happening in some less than 30 seconds, in reality, it is going to take a lot of time to do this. Therefore, it is still not acceptable by some users, whereas some users would accept it. So who are those users who accept and who are the users who do not accept? Let us see. Indian Railways itself cannot accept this, right? Because if there is an interruption for 40 minutes, all the trains which are running on electric supply would not get supply. They have to stop. And 40 minutes, you cannot stop a train. It will be running away from the schedule. So that means this is not suitable for a user like railway. Whereas for a user like a electricity board who is working on medium voltage, 11 kV or where the users are not dependent on electricity, then the people can wait for 40 minutes. It's not an issue. So depending on this kind of user-based requirement, the system will be adapted. So it's not like this system has failed. It's like this system is for a certain type of users. Then what is the other system which will have a foolproof method? So let's see the next example. 1.5 breaker arrangement. So let's understand what is the system. You have same 2-bus arrangement, but the drawing is like this. You have 3 breakers connected like this, 2 isolators. So like this, it keeps on going, bay 2, bay 3, bay 4, etc. So bay 1 is connected like this. It is supplying both the bus bars. It comes here and goes out. So this can be bay 3, this can be bay 4, etc. I have not written here because in our example we are discussing only 2 bays. So it's actually a parallel path. Supply goes to bus 1 as well as bus 2. Comes from bus 1 as well as bus 2 like this. Now let us create a fault in bus 1. Same fault. What happens? Which breaker we should trip? So from the drawing, you can see that all the breakers connected to this bus 1 should trip. So it will trip in this manner. The relay will be designed to trip these 2 breakers. When you trip this, you can find that there is another path through which the supply is already flowing. That means there is very less duration of disturbance. The duration of disturbance is going to be in terms of milliseconds because the breaker operation time is going to be in milliseconds. So typically a breaker operates in 40 to 50 milliseconds. Even if you assume it as worst case, double the time. 100 milliseconds, we should be able to trip these 2 breakers and clear the fault. So you can see here, earlier we took 40 minutes, but now we took only 100 milliseconds to satisfy this protection principle. Therefore, the 1.5 breaker arrangement is one of the superior category. However, we don't use it everywhere because you can see there are 3 breakers for 2 lines, whereas in the earlier example, we had only 2 breakers for 2 lines. Just see this example. For 2 lines, bay 1 and bay 2, this bay is also called as a line. So 2 bays, you have only 2 breakers. Whereas here, for 2 bays, so you have 4 bays here. We have shown 2 bays here. Bay 1, bay 2, maybe bay 3 or bay 4. You can do a different name. So you need 3 breakers for 2 bays. So 3 divided by 2, it's 1.5. That's why it is called as 1.5 breaker arrangement. It's an expensive solution because what you are seeing here is a single line diagram. In reality, this is RYB, RYB, RYB here. That means 9 breakers. So it's a very expensive system. So we have both the systems currently in use. So for users who can wait for 40 minutes or 30 minutes, depending on the number of isolators in their system, they can go for the previous arrangement. So technically speaking, this is the best. But whether you want to use a computer in a calculator mode, it's a very expensive solution. So it's in the same way. There is a balance between technical requirement and commercial requirement. Based on that, the user is free to choose which solution they want. So from this understanding, we conclude that this is the protection classification using the principle called as faulty portion should be disconnected when a fault occurs. Healthy portion should not be disturbed when a fault occurs. Next is we are going to move into a different classification to better understand the protection principle. So far we have not seen the protection concepts, we have only seen the fundamental principle. Protection classification. There are total 95 types of protection system. So why I am telling 95? What is the syllabus? What are the names of this 95? So this is actually called as ANSI code, ANSI, ANSI, American National Standard Institute. So ANSI has defined 95 names. So you can just Google it, you will get the complete list. But once you understand the fundamental formula, it is very easy to read all the 95 and understand easily. So in maybe 1 or 2 months, you can understand the entire 95 classifications. But here what we are going to see is, we are just going to classify this 95 into 2. Either it will be in the left side or it will be in the right side. So this 95 can be divided into left hand side or right hand side. So let's see the major classification. We classify this as unit and non-unit protection. So this 95 protection which we are talking about, it can either be in the unit protection or it can be in a non-unit protection. So let's understand what is this unit protection and what is this non-unit protection. Let's see with an example. Let us say you are in a hotel. You are staying in a hotel. This hotel is protected by a security. Normally when you go to any hotel for check-in, you have a security system there to scan your bags and they ensure that you don't bring any dangerous equipment inside. So it's for the safety of the hotel and for all the people staying inside. This security will protect only the area inside the hotel, not the area outside. So that's the understanding that we need to register. The area which is protected by this security is actually defined by the compound wall of the hotel. Anything happening within the compound wall, the security is going to protect. Anything outside the compound wall, the security will not do anything because it's not his area. And to protect that, it's the work of the local police. So let's come back to this. You can keep this example to understand this protection classification. It's very easy. The security whom we are talking about is actually the relay. The relay is a protection device. It's going to protect. The compound wall, which is defining the boundary of the unit in the hotel, is actually the current transformer, CT. So this is about the unit protection. So unit protection means we are going to protect a specific area. And who is going to protect? The security. That security is none other than the relay. The relay is the protection unit. And it is going to protect a specific unit. That unit is going to be defined by the CT. The area covered by the CT is the unit which we are going to protect. So if there is no defined boundary, then it will become a non-unit protection. You can say the security of the hotel has a boundary, whereas the police is actually having a larger boundary. We cannot say the police doesn't have a boundary. Even they work on a specific area. And bigger than the police, you can say the army, that's having a very big boundary. So it's actually how big the boundary is. So in power system protection, this unit protection or the boundary which is defined is actually called as the Merz price scheme. It has multiple relaying points, whereas in non-unit, it is having only single relaying point. This is how it is. So there is an equipment. Here the equipment is transformer. It can be anything, motor, generator, transmission line, or any equipment in between these CTs. So these black, this is your CT. And this is the pilot wire. So any faults occurring here between the CTs, it will change the direction of the current. So there is a current direction which happens like this. When the current is flowing like this, it will flow in the opposite direction like this. Or maybe I can assume that the supply is flowing in this direction, in the primary. Normally, the CT secondary current will flow in the opposite direction. This is as per the dot conventional principle. The secondary current will always flow in the opposite direction of the primary current. Or you can always say that the CT secondary is earthed towards the protected equipment. So when the primary currents flow from the winding to earth, the secondary current flow from earth to winding. So you can see here, this would be your earth connection, your start point CT connection. So primary, earth to winding, secondary, winding to earth. Primary, winding to earth, secondary, earth to winding. And your CT start point will always be earthed towards the equipment that we are protecting. So this is the dot conventional principle. According to this, you can follow this arrow mark. You will find that it flows like this. And you can follow this arrow mark. You can find that this is flowing like this. And this is the relay. So that means what? In the relay, the current is opposing each other. Current flows in the opposite direction. So let us say both are having a CT secondary ratio of 1 amps. That means your full load current is 1 amps. So 1 amps flowing here, 1 amps flowing here. 1 minus 1 will be your differential current, that is 0. When there is no fault, the current will be 0. That's what is read by the relay. Now let's say there is a fault outside. A fault occurs here. Fault at F1. Because of fault, let us assume that the magnitude increased to 10 amps. Earlier it was 1 amps, now it is 10 amps because of the fault. Now you can see, does the primary current direction change? No, it does not change. It still feeds the fault. If the primary direction does not change, the secondary direction does not change. That means 10 minus 10, it's still 0. The relay reads 0 current, even for a fault. But you can find that the fault is outside the CT. Therefore, the relay does not read any fault current. Let us see a third example. I will make another color. This time, let me make it as pink. Okay, a fault occurs here. Fault at F2. When this fault occurs here, this direction changes. Because fault current always chooses the least resistance path. This already flowing towards the fault. This current also starts flowing towards the fault. So if the primary current flows from left to right like this, winding towards, the secondary also will change the direction. So now this direction will become like this. So this will flow like this. If this flows like this, you can see it is adding. That means 10 plus 10. Now it will become 20. So what we find here is when the fault is inside, that is between your compound wall, inside your CT, the current direction changes as defined by Morse-Price scheme, and the relay will issue a trip command. So the direction of current is actually defined by the location of your CT. So the CT can be imagined as the security camera in a hotel. A security just sits in one place, but he can monitor the entire hotel in all the floors and in all the compound wall everywhere using security cameras. So that means the security camera is your CT. The place where we position this current transformer is very, very important. Okay. So let's understand the next part, that's non-unit protection. The single relaying point. So let's understand the story first. When this unit protection is working so perfectly, what is the need for non-unit protection? So let's go back to the same example. The hotel. So two people fighting inside the hotel. The security will go and protect. Two people fighting outside the hotel. The security will not do anything because that doesn't disturb the hotel. Now let us say somebody is placing a bomb outside the hotel. Now what should the security do? It is not inside his hotel boundary. It's not inside the compound wall. He is doing something outside. But at the same time, it is understood that if the bomb blasts, it is going to affect the hotel. So this bomb is actually nothing but the magnitude of the fault current. So what we understand from this example is, if the magnitude of the fault current is very high, then even if the fault is outside the boundary, that is outside F1, still the relay should trip. If the magnitude of the fault current is small, then relay trips only for internal fault, not for external fault. But if the magnitude is very high, then even for external fault, the relay will trip. That is the exact requirement. And to satisfy that, we go for non-unit protection. So this can be a transmission line or any equipment. So what we connect is, we connect a current and a voltage transformer to a relay. And from here, this is called as the relaying point. So these two provide only one information to the relay. This CT provides current and the VT provides voltage. And we divide voltage by current. We get impedance, Z. So we are using only one measurement, that is called as impedance measurement. Hence we call this as single relaying point, because we are only measuring only one parameter. Whereas here we have two CTs. This is measuring one current, this is measuring another current. We are subtracting the quantity. So we have multiple relaying points. You can have 3 CTs if it is a 3-winding transformer. You can have 10 CTs or 20 CTs if it is a bus bar. So multiple relaying points will be there. Whereas in non-unit protection, you will have only one relaying point. This is going to calculate the impedance. So for impedance, you have two formulas. What are the formulas? Z is equal to V divided by I. You can also say Z is equal to R plus J X. So you have two formulas for impedance. Ohm's law, Z is equal to V by I. Another formula, Z is equal to R plus Jx, resistance and reactance. So this we call this as settings, ZS, set impedance. This we call it as actual impedance or measured impedance, Zm. So here what we do is, whenever your measured impedance is less than your set impedance, then it is a fault. If your measured impedance is greater than your set impedance, your system is said to be healthy. Okay, let's understand here. What happens when a fault occurs? Your voltage comes down and your current increases. So when your denominator increases, what happens to your Zm? Decreases. That's what we see here. During the time of fault, your Zm reduces than your set impedance. So this set impedance is actually the resistance and reactance of your transmission line or of your equipment. So when your measured value is less than your set value, it's a fault. If your measured value is greater than your set value, your system is healthy. That means your current has crossed the impedance and gone out. If your measured impedance is not crossing, that means it's inside. It has not crossed that area. It is just flowing here itself. I remove all the drawing and let's see what are the challenges that they face. The unit protection is affected by CT error and the non-unit protection is affected by CT and PT error. The solution is modern CT saturation detection algorithm, high-end slope characteristics. Here the solution is pilot-aided scheme and non-pilot-aided scheme. So these are the two types of classification. If you have understood these two, you can understand all the 95 types of protection function in ANSI code definition. Even the protection function defined in Indian Railway, we will come to that after this presentation. Whatever falls or different types which is defined in Indian Railway comes under either this unit protection or non-unit protection. These are the different types of numerical relays, the most commonly used in India. So far we have been talking about the relays. A relay is used for protection. So this is how the relay looks. And in railway we have something different. That is because it's working on single phase mode. These are working on three-phase mode. So understanding the single line diagram. So in Indian Railway, I think one of the largest network in the world with the 63,000 track kilometer, and we are proud to be owned by a single entity. I hope it's more than 25% is electrified and the balance is working still on diesel. So what we are talking about is 25% of the 63,000 track kilometer, which is running on electricity. And to do this, we have different types of locomotives, which you are already aware, like WAP, WAM, WAD. So depending on the diesel locomotive or mail and express or passenger or type of AC current, DC current, which is in the famous Bombay Thane section. So from the nomenclature of the locomotive itself, you will be able to understand what is the type of feeding, what is the type of gauge, is it broad gauge, meter gauge or narrow gauge, and what is the type of hauling capacity of the locomotive. Is it used for goods train or the passenger train? And you also have trial locomotives, double locomotives pulling heavy load in goods train. So this is very, very important to understand. It may sound like more mechanical and civil, but actually both all put together is required to understand when you are trying to protect the power system network. Because when you have two locomotives, that means you have two transformers inside. When you have two transformers inside, we are talking about two impedance in parallel. When we talk about two impedance in parallel, and that too it's moving, it's not fixed. A moving impedance comes into my transmission line network. That is your 25 kV line network. So if you have a moving impedance coming into the network, the relay should be aware of what is happening. What is the impedance moving? How much is the impedance? Because we are comparing the set impedance with the moving impedance or the measured impedance, V by I. So the relay is finally measuring voltage and current and calculating the impedance. So we should also be aware of what is the impedance in the locomotive. And that impedance is actually dependent on the load which is carrying. If the load is small, you don't need two locomotives. One locomotive is sufficient. If it is a passenger train, you are not worried about heavy torque. Speed is more important. So high speed and less. So WAP may be having a different locomotive impedance compared to WAG. So which transformer impedance we are talking about? This plays an important role. So this comes later stage to understand. So currently you can see the network. The incoming for the railway is like this, either 66 or 132 kV, something like this. So it feeds the transformer. The transformer converts this dual phase, that is two phase, into single phase. And this single phase is connected to a bus bar. And this bus bar has one end buried to the earth and the other end is actually fed like this. So through a bus coupler, so that you can feed this transformer to this section or this transformer to this section. And from here, using a BP, it's connected to the tractions line up and down. So it's divided into multiple sections actually. So the moment we talk about sections, what is the need for section? So you cannot run the entire feeding from one traction substation for 100 or 200 kilometers because of the drop in voltage. So every after every 30 kilometers or 40 kilometers, we need to keep changing the source of the supply. Or you can even say we cross from one state electricity board to another state electricity board. So different transformers from different state electricity boards are actually feeding the railway network. So when we say different transformers from different state electricity boards, then we need to ensure that our system is actually not shorting any of these phases. Let's assume that here you are taken in RY. In another traction substation, you have taken in YB. So when the locomotive is moving, the top current collection part, which is called as the pantograph, should not short this section. So neutral section concept actually provides how to cross the sections without shorting the overhead transmission line. So no load voltage, I think it's around 27 kV, and it goes up to 25 to 23 kV depending on the load consumed by the locomotive. So our main intention is protecting this transmission line. And what we have understood is protecting the transformer and this three-phase transmission line. So this three-phase transmission line is actually protected by the state electricity board as well as from your traction substation. So this would be a three-phase protection. Here it would be two-phase. And you will be having CTs here located. You can see the CTs windings. So using this winding, we will provide single phase differential to this transformer also. So you can see the transformer is actually provided a unit protection, and this transmission line which is coming from this line to the transformer is provided with a non-unit protection. The same thing concept which we discussed earlier. Characteristics such as parallelogram characteristics. So this is very simple. This is the same what we have seen in the previous example. If you recall, we spoke about Z is equal to R plus JX. Z is equal to V by I. And we called Z is equal to V by I as measured impedance, Zm. Z is equal to R plus Jx as set impedance. Okay, let me write down here. It will be more clear. Zs is equal to R plus Jx. And Zm is equal to V by I. When a fault occurs, voltage reduces, current increases. What happens to the impedance? Comes down, because the numerator is bigger than the, denominator is bigger than the numerator. So from this we can define like this. Zm less than your Zs is your fault scenario. Zm greater than Zs. The system is said to be healthy. This can be equal to also, less than or equal to. Okay, so this is electrical understanding. What you see here is electrical understanding. This is a comparator, a logic, mathematical understanding. Now we are shifting it to a graphical understanding. So what we have done here is Z is equal to R plus Jx. We have drawn this Rx plane, and this boundary, this line, you see here, this line is your Zs. So the line that you see here is actually a plot of this Zs. Now what we do, we measure the voltage and current in the relay, and we will keep a point, Zm. Okay, let us say I have Zm as 10 angle 25. So you can convert it to either in polar or rectangular form, and you can plot 10 angle 25. 5 angle 80. 5 angle 80. Okay. Like this you can keep on plotting. And this plotting work is actually the work of the relay. Now what it does is, it will check this in a graphical way. whenever it is plotting inside this graph, it's a fault. Whenever it is plotting outside, the system is healthy, because that's what we see here. The measured impedance is greater than the set impedance. That means it's outside. Yeah, here it is outside. Outside, outside, healthy. When it is on the line, that's why I have put one equal to symbol here. When it is exactly on the line, or it is inside, less than, then it is a fault. So this is what we are trying to do in testing a distance relay. We draw these characteristics as defined by RDSO. So RDSO has defined that they need parallelogram, whereas power system has lot of characteristics. It has quadrilateral, more lenticular. So all these things you might have studied in your syllabus in engineering. So it has a wide range of characteristics, out of which parallelogram is adopted in Indian Railway, because RDSO has defined this. So this is the real-time understanding of how the impedance parallelogram characteristics is achieved. Now you can say another important point, inrush current, charging current, or you can say the starting current of motor is very high. We all know this. Starting current of motor is very high because of the absence of back EMF. Another point, when you charge a transformer, there is a very high inrush current. So all these things happen for a short duration, right? So when you say starting current of motor is high, it is only for few milliseconds, maybe 1 second, 1000 milliseconds, it will be high. After that, it will become normal. Charging of a transformer, the transformer will take sudden current, and that will be for a short duration, not for a very long duration. So maybe 250 or 300 milliseconds. Then after that, it is going to come down. Now, why we are discussing about this is, during that short duration, we are actually creating this scenario. So whenever you charge the traction motor, what is happening? There are 6 traction motors in a locomotive, right? So when you read about bogies, Coco bogie, Bobo bogie, so you will know that Coco bogie is something which is used in electric locomotives. So that means you have 6 axle. Every axle has a traction motor. So when you have 6 traction motors connected to parallel DC bus or AC bus, depending on the type of locomotive, you are actually charging all the motors simultaneously. They are kept in parallel. Then imagine the amount of starting current that is going to be absorbed. During that time, there will be a suppression in voltage and increase in current, which will result in impedance. And if this happens, you may result in this scenario. This scenario means you will plot something inside. If you plot something inside, what happens? The relay will trip. If the relay trips, you will never be able to start your locomotive. Therefore, the concept of differentiating between a charging of a locomotive and a real fault comes into picture. So it is found that the charging of a locomotive is more resistive in nature. That is, in R plus Jx, the R value will be more. So this is called as load encroachment. So load has encroached into the impedance characteristics, and therefore the relay should not trip. That means we have to cut this area. So to cut this area, we will create a graph like this. This red line that you see here is actually called as load encroachment. So based on the study created by RDSO, they would have defined that whenever you charge a locomotive or a locomotive moves from one section to other section, this is the amount of load current that will encroach, and that will stop here. It will not go inside here. So it will not go here. It will stop here. So that means till this point I have to cut from this parallelogram characteristics. This is called as load encroachment. So I am deleting everything. Different types of protection system as required by railways: zone distance protection, wrong phase coupling, PT fuse fail alarm, intelligent auto reclosure, disturbance recorder. Delta I. Two types of protection in delta I: scalar delta I and vector delta I. This is for a sudden change in current, that is called as delta. So this is also identified by the relay. Okay, so this is a very interesting area to discuss. This 26 pages specification RDSO, maybe you have the latest spec also, you can use it, but the fundamental never changes. The spec normally talks about, when you are buying a equipment, what should be the specification of that equipment. So there will be some advancements in every new specification. However, the fundamental protection system is always maintained. So when you move into the specification, it defines the list of protection functions required. So let us go to it one by one. A transformer. When you want to protect a transformer, what are the list of protection that you need to provide? These are the 5 list of protections that you need to provide. Differential relay. This is the same Merz price scheme of differential protection or unit protection that we spoke about. IDMT overcurrent relay. IDMT stands for inverse definite minimum time with 2 stages, 2 independent stages of overcurrent. One for HV and the other for LV. So this is actually the non-directional principle. That is non-unit protection. So the unit protection will provide protection for all the faults which is happening inside the transformer. That is between the CTs. If there is a fault outside the transformer, away from the CT, and if the magnitude is high, then we provide a time delay and wait for some other relay to operate. If no relay is operating, we will trip. This is called as IDMT, inverse definite minimum time. It means greater the fault current, lesser the trip time. Lesser the fault current, greater the trip time. This is called as IDMT. For this, several curves are there. We normally coordinate. This is called as relay coordination. That is, if you have 2 relays, if relay 1 stops, relay 2 will not trip. If relay 1 fails to trip, then relay 2 will trip. That means relay 1 should have, let us say, 1 second delay. Relay 2 should have something more than that, 1.5 seconds. Then only I allow the relay 1 to trip. So allowing the previous relay to trip is called as IDMT. They are called as relay coordination. IDMT is one of the tools to do it. The third protection, earth fault, instantaneous earth leakage system on HV and LV. So high voltage side as well as low voltage side, if there is an earth fault, current flowing to the ground, that also can be detected and found. This again is non-unit because this doesn't pertain to any specific area. If you pertain to a specific area, that is, you restrict that to a specific transformer alone. If the earth fault occurs inside the transformer, it is called as restricted earth fault. That means restricted earth fault is a unit protection. Earth fault is non-unit protection. So here we are just saying instantaneous earth fault. That means it is a non-unit protection. High-speed intertripping relay. So this is not a protection function. It is an additional function used to help the protection function. So high-speed intertripping relay. Normally we call this as master tripping relay. The last one is auxiliary relay for transformers. Buchholz relay, winding temperature, oil temperature. So these are the things that you might have seen. Buchholz, it is a gas actuated relay. We normally keep this relay on top of the transformer itself. So whenever a fault occurs inside the transformer, because of the fault, there will be some kind of heat or fault current, all these things generated. So due to that, bubbles will follow. Bubbles will be formed inside the oil. So when bubbles form, what happens to the bubble? It will by nature move towards the top because oil is heavy. Bubble will be light. So bubble will move from the bottom to the top. So when it is moving, in the path we are keeping one relay called as Bockol's relay. This relay will catch the bubble and it will identify what is the gas inside and it will issue a trip command. Depending on the contents of the gas, how much methane, how much ethane, how much nitrogen, how much oxygen, how much hydrogen. So depending on the analysis of this, we can also say what kind of fault has occurred inside the transformer. This is called as oil diagnostics or transformer life management system. I am not sure, this is not much popularly used in railway, but in because we are using a small 25 kV single phase transformer, we are working only in medium voltage. This is for extra high voltage transformers, 400 kV transformer, 765 kV transformers, and high MVA rating, 300 MVA, 325 MVA. This is a solution provided, that is transformer life monitoring. Here it is just tripping. It will just get the gas and it will trip. That's the work of Bockol's relay. It will not analyze what is the percentage of each gas and it will not try to tell what type of fault. So here it is just used as a relay. And the winding, the transformer has a winding inside. We can identify the winding and the oil temperature. So next is, what are the list of protections required for overhead line? Feeder protection, polygonal characteristics distance relay. Okay, so earlier in the presentation we saw parallelogram characteristics. A parallelogram is also a polygonal characteristics. So you need a distance relay. It's nothing but a non-unit relay, which we have already seen. Measured impedance and set impedance has to be compared and protected. Next, wrong phase coupling. Okay, so let us see what is wrong phase coupling. So from here you can understand, this is IOL, insulated overlap, or a neutral section. So I think you are well aware how the neutral section is working and how the insulated overlap is working. Suppose this section and this section is live and connected to different transformers. And if a locomotive is going to short these two sections together, it means you are coupling two wrong phases together. Okay. The other one is, if you are having a neutral section, that means it's not an insulated overlap. So I move from the live to the neutral, from the neutral to the live. So during this movement, the loco pilot or the engine driver is supposed to trip the DJ or the circuit breaker located on top of the locomotive. So I think you might have read this. You see a diamond board like this, 500. So this, I think, no, when you are traveling by train, we will see this. Then another diamond board, which says 250. Then another 3 lines, trip DJ. Then after some time, close DJ. So in between this is maybe 20-30 meters, which is normally in the slope or in level, not in upstream. And the train is actually going to be running as a coasting. That is, coasting means without any supply, the train will be moving from one location to other location because of the momentum. So what is this board? This means after 500 meters, there is a neutral section. So you will have a transmission line like this. It goes somewhere up. A new transmission line comes here, goes somewhere up. Another new transmission line comes here, and it routines. So this is your section 2. This is your section 1. Both can be from different feeding substations. This is dead section, neutral section. So you can see. So when a pantograph comes here, it moves like this. The pantograph is actually having a compressor inside, which is pushing the pantograph at a certain pressure. Because if the pressure is not there, you will find sparking at the pantograph. So to prevent sparking, it is actually pushing the overhead line. So if this line is going up, and if this neutral line is not there, this pantograph will go up. So to prevent that, we have a dead section, this neutral section. But if the DJ is not opened, DJ means circuit breaker. I think it's a disjoint, a German language. So this DJ has to be tripped. If you don't trip that, you are moving from live to a dead section. And during that time, heavy sparking will occur. This is called as panto flashover. So panto flashover and wrong phase coupling, both are two different concepts. Just to understand, I have given an example. There may be several other live case examples which your team would be sharing with you during your training program. So a locomotive driver who sees this board understands that after 500 meters, he has to trip the breaker because there is a neutral section. Here, this means after 250 meters, there is a neutral section. Here, he is supposed to trip the breaker. So this is the procedure followed by the loco pilot. However, accidentally, if he fails to do that, huge sparking would occur. And to identify that sparking and trip the breaker, panto flashover protection would be provided. So that's about wrong phase coupling and panto flashover. Maybe it comes later. Okay. Yes, the third one, panto flashover. So next is PT two-stage overcurrent relay. So it's just a overcurrent function. It acts as a non-unit protection with a definite time. So earlier we saw IDMT, inverse definite minimum time. That is for transformer. For catenary wire, that is 25 kV line is called as catenary wire. We have to provide definite time. The difference between definite time and inverse definite time is definite time is only based on a current crossing a specific threshold. For example, 2 amps, let us say. The moment current crosses 2 amps, the relay will start a timer. At the end of the timer, it will trip. This timer is going to be fixed. It can be, let us say, 5 seconds. Let us say, example. Whenever the current crosses 2 amps, in 5 seconds, the relay will trip. This is called as definite time. Then what is IDMT? In IDMT, whenever the current crosses 2 amps, a timer will start. But what should be the time? Is it 5 seconds? It is not 5 seconds. It's actually dependent on the magnitude. For example, let me say, if the current is 10 amps, trip in 1 second. Or if the current is 5 amps, trip in 3 seconds. So you can find that the time keeps changing depending on the current. The greater the current, the lesser the trip time. The lesser the current, the greater the trip time. So this is the difference between IDMT and definite time. So next one, PT fuse failure. What is PT fuse failure? So we already saw in the impedance section, Z is equal to V by I. So Z is equal to V by I means voltage divided by current. The voltage which is connected to the relay is connected through a PT. connected through a fuse. This fuse, if it blows out, what will happen? The relay will not read any voltage. If there is no voltage, what happens? Z is equal to V by I. V becomes 0. That means Z becomes 0. If Z becomes 0, your measured impedance comes inside the drawing. Zm is less than Zs. And it will be treated like a fault. Whereas it is not a fault because the fuse only has failed. Therefore, the protection will be blocked whenever the PT fuses fail. Which protection will be blocked? Only distance protection will be blocked because that is only dependent on voltage. This overcurrent C is actually not dependent on voltage. Therefore, it will be working as a backup. So this is called as PT fuse fail relay. Nowadays, all these functions are in a single relay. One numerical relay has all these functions. I think for vector delta I and panto flashover alone, you have separate relays. Of course, there are single relays, but as per the railway spec, it is being provided as separate relays. Next is the vectorial delta I relay. Vectorial delta I. High resistance earth fault cannot be detected by distance protection relay nor overcurrent relay. DPR means distance protection relay. OCR means overcurrent relay. When there is a high resistance, what we see? Ohm's law. Z is equal to V by I. So I is equal to V by Z. If your impedance resistance is very high, Z is very high, your current will be very low because they are inversely proportional. So when the current is very low, your distance protection relay will not pick up. And overcurrent relay also will not pick up because the current is low. So in this kind of situations, these two relays cannot identify the fault. Therefore, the backup is delta I. This delta I is working on rate of change of current and harmonics. Why harmonic comes into picture? We already saw an example. Whenever you start 6 motors in parallel, starting current is high. Whenever a train suddenly enters into a section, the amount of current withdrawn will be high. Therefore, how you will differentiate between a fault and a movement of train? So to do that, we use harmonics. So how does it work? You can see here the next line. When there is load, harmonics will be there. That is, when there is a locomotive traveling, harmonics will be there. Whereas fault will be pure sine wave. This is the definition of RDSO. Some examples they have mentioned. Conductor falling on a rocky terrain. So rock, it's not a perfect conductor. It's not going to be having a very high, very low resistance and a very high fault current. Therefore, that's an example. The only delta I can detect. Dry twig touching a overhead line. So, railway being such a vast network, the overhead line will be passing through the forest areas. So, some trees may touch the overhead line because of wind in unmonitored sections. So, a tree will be a very high resistance. That time, this will happen. Monkey or birds or insulator problems. So, monkey is jumping on transmission line and hanging because of that, the line getting cut. Open circuit, like bonds not connected or open. So delta I can protect fault current up to 200 amps. That's in primary. Two types as mentioned, scalar and vector is also shown here. Panto flashover we have already seen. So next is the last one, shunt capacitor bank. So this is for power factor improvement. And what are the list of protection? It's very simple. You can just see IDMT we have already seen. Over voltage, it's also very simple. Whenever the voltage crosses the set value, it's going to be over voltage. If it is below, it's going to be under voltage. Unbalanced protection. So the capacitor bank would be on 3-phase. So when there is a unbalance created in the RYB, it will be able to identify. In case of single phase systems, it is the current unbalance before and after the system. Internal fuse. So this is like the fuse failure which we have already seen. So if the fuse fails, then your capacitor actually comes down value. So therefore the fuse also has to be identified properly. So you can see we have covered all the protections required for railway as per the railway specification. So you can see from page 14, they have written in detail on polygonal characteristics. What are the things that it has to happen? What should be the values? So almost 80 to 90% information will be available. This is one of the very simple document which I have seen. Very clearly written, and it's wonderful to understand the protection concepts. So this area, load area, you can see the shaded area. We saw load encroachment earlier. Let's see two important concepts. So in the specification, we have seen all the protection functions. In majority of the protection functions, or almost in 100% of all the functions, we are using current-based principle. That is, here CT is one of the basic requirements. For distance, we use both CT and PT. For overcurrent, for WPC and many other things, we are using the current transformer. One big challenge which we face in a current transformer, this is a very, very important concept. This concept is called as CT saturation. Okay, so let's understand what is a CT saturation. So CT saturation means, we can take an example. You have a 1000 or 1 amp CT. Okay, this means in the primary, if there is 1000 amps, in the secondary it is going to be 1 amp. So when it is 2000, it's going to be 2 amps. 3000, it's going to be 3. Now this is theoretically true, but in practice, we will be getting some error would be there, right? When it is 4000, 5000, next 7000. So what you see here, when we have a 1000 bar 1 amp CT, assume that this is your full load current. Okay, and we are going to get 3 kinds of situations. This is your first situation. This is your second situation. Okay, you can call this as area 1. This, let's call it as area 2, and this call it as area 3. You can find that here also there will be some error, but it's very, very minimum. Maybe let me put some error here. Okay, some amount of error is there. In this area, error increases. For 2 it is 2.01. For 3, error increases by 0.2. 4 it is more. 5 it is more. For 6 it is more. Then beyond that, you can see as you increase the current, here there is no much change. It is just almost same like what you are seeing here. So this is called as the saturation region. This is called as CT saturated. Once your CT is saturated, it will not respond to further increase in primary current. Now this need not be 6000, 7000. This is just an example. In reality, it may be 15,000 or it may be even 4,000. Depends on the CT which we are selecting. The differential protection, the Merz price scheme protection or the unit protection which we discussed earlier, is actually purely working on CT only. Between the currents, incoming current, outgoing current, it is subtracting. So if you are getting so much error, then when you subtract, it will not be 0. It will be having some error. So because of that error, the relay may take a wrong decision. That is, instead of keeping quiet, that is during a healthy situation, the relay may trip. Therefore, identifying this situation and working in line with this situation is very, very important. So how to address that? So for this, two concepts were introduced. The first concept is ID is slope I1 plus I2. This we already saw. This is called as differential current. In addition to this, one more concept is there. This is called as IR, restraint current or bias current, which is equal to maximum of I1 and I2. This can also be said, this can also be written as IR is equal to average of I1 and I2. It can also be sum of I1 and I2. So like this, there are several formulas: modulus, minimum of, maximum current. So like that, several formulas are there. Which formula we should use? That actually depends on the numerical relay. It is an inbuilt algorithm. So from this concept, what we understand is, because of the error in the CT, and that also the error is not working in the same way. It works in 3 different ways in 3 different regions. Area 1 error is different. Area 2 the error is different. Area 3 the error is different. So in 3 different ways it is working. To adapt it to these 3 different types of errors, a formula called IR is introduced. And what was done is, ID and IR was plotted in a graph. IR, restraint current, ID, differential current. Okay. So now let us see what happens is, from 0 till 1000 amps, that is still the full load current. The current is having a specific type of error, and this error is fixed. It will not change. This is defined by your CT manufacturer. So let us say the CT nameplate detail says that this CT has an error of 0.01%. That means it is up to full load current. Your error will be constant. So when I draw a line, let me draw a blue color line. When I draw a line, my error is constant up to a specific value. Okay, that is your blue region. After that, my error will increase in a uniform pattern. Let me do that in brown color. Now I am going to put brown color. Now brown is going to, error increases in a uniform pattern. Okay. Then later, this region comes in, saturation region. In saturation, let me use green. My error is very, very high. Okay. Now when I draw this area is A1. This area is A2, this area is A3. So saturation region. IR means do not trip. ID means trip. So when you plot these two values together, you will identify whether you have to trip or you should not trip. Let's see an example. This one, let's call it as breakpoint 1. Normally this will be your full load current, because up to full load current 1000 amps, you are in A1. Then your CT saturation current, this is called as breakpoint 2. So in breakpoint 2, after BP2, you will be in saturation region. So what we have done, the electrical understanding which we had here, this we have graphically transformed here. Now you have so you have a system like this. Now let us say you have 1000 amps flowing here, and you have 1000 amps flowing here. Assume this is a transmission line, not a transformer, so that it's easy for us to calculate. So 1000 amps in the primary and 1000 amps in the secondary means, what will 1000 amps in the primary means it's 1 amps in the secondary, 1.001. So assume what is your ID. Find out what is your ID and IR for each case. Your ID is 1 minus 1. Okay, I have written plus. Plus means you have to make it as vector addition. Okay, it's a vector addition. So you can assume an arrow mark like this on top of each other. Okay, so either you use vector addition or you can use subtraction. So what is 1 minus 1 or 1 angle 0 plus 1 angle 180? It is going to be 0. Okay, my ID is 0. So here I will plot 0. or because of this error, let us say 0.02, 0.01 error in both the CTs. So 0.02 somewhere here. This value, before that, let me write this value. 0.2 pickup, let's say it's 1 per unit, and let's say it is 6. Okay, 6 per unit. So 0.02 is your ID and your IR. Let us assume maximum current principle so that it is easy for us to understand. That is, calculation will be easy. So in maximum current, which current is high? One side is 1.001, other side is also 1.001. Which is high? Answer is 1.001. So plot, you have to plot this value, 1.001, 0.02. I have to plot this value, x-axis, y-axis. So when I plot this, where do I plot? 1.001, somewhere here, 0.02, right? So let me put it in red color with a uniform small dot. It's somewhere here. Okay. Now it is below the curve, below these 3 lines. So your system is healthy, no fault. Okay. Now let us assume a fault. Now where is the fault? Let us assume an internal fault. If the fault is here, and let us assume 2000 amps flowing in both the CTs. And because of the fault, it is going to change direction. Fault is inside. So 2000 plus 2000. So 2000 plus 2000 is 4000. So 4 amps is my differential. And highest is 2000. So it will be 2, 4. Right? 2 amps is my restraint current because both sides are reading 2 amps. And when I add both of them, it will be my differential current. So ID will be 2. So here I can say IR. Here I can say ID. So let me write it again. My restraint current is 2 amps maximum. And what is my differential current? 2 plus 2, 4 amps. So plot 2 and 4. 2 somewhere here, 4 somewhere here. Relay will trip because it is plotted above the curve. Now let us take an example 3. Fault outside. Here. Fault is here. Let us assume same 2000 amps. So since the fault is outside, this direction will not change. We already saw this. So if the direction is not changing, what will happen? Your differential current will be theoretically 0, practically maybe some error. And your restraint current is still 2 amps. Right? 2, 0.02. So let's plot that. 2 is somewhere here. And 0.02 is definitely below the curve. So that means you can see the relay does not trip because it is below the curve. Now what happens when the CT saturates? So far we were talking about 2000 amps. Now if you assume the fault current to be 8000 amps, the same thing holds good. So let's say the CT saturated, one side CT only will get saturated. Both the CTs will not get saturated. If both the CTs get saturated, there is no problem. Your system will work perfectly. Because 6.22 minus 6.22, it will again be 0. External fault CT saturation, relay will not trip. 6.22 plus 6.22, relay will trip. Internal fault CT saturation. So there is no problem. But the problem occurs when only one CT saturates. That is the worst case scenario. So now let us understand how do we work for this. So when one CT, let us assume fault current is 8000 amps. One CT is reading 8 amps in secondary. Other CT is reading 6.22. Okay. Fault is external. External fault. What should happen? Your relay should not trip. Okay. So external fault, what will be your current? 8 amps, 6.22 amps. The fault is external. That means 8 minus 6.22. How much it is? 8 minus 6 is 2 amps. So 1 point some value. 1.8. let's say 1.8. This is my, differential current. What is your restraint current? One side 8, 1.6, one side is 6.22. So your maximum current is 8 amps. 8. So plot 8, 1.8. So this point is going to be 8, 1.8. So somewhere here it will still be below the curve. So you are able to understand this 8 is more than your saturation point. And when we move towards the saturation region, we have created more area for restraining from tripping. This is called as the CT saturation algorithm. This is widely used in all the type of relays, in all the type of protections which involves unit protection. Even non-unit, it is applicable. Okay, so let me move on with the specification. Yeah, I wanted to show you the videos so that you can start using. If you want further information, you can directly view them to understand. So we have created these kind of videos. These videos are available online in YouTube, and we will provide an access file at the end of this presentation. And you can just scan it from your mobile and you can watch it in YouTube. It's available for free. How to test each and every protection function: impedance, characteristics, timing, reach test, minimum operation current, PT fuse fail, switch on to fault, overcurrent. Okay, I think few things, auto recloser, SOTF, these few things we did not see in the specification, or we did not read the specification fully. So we were not able to see this. So let me show you. Since you are having the video, you can directly understand what it is showing. Let me show you 3 things and maybe auto recloser. You can understand how we have tested it.
In this video, we are going to see how to test the distance protection function. So before starting the test, we have to check the settings. So navigate to distance protection. So you can see I'm able to see values like RF1 5.59, XF1 19.08, RB1 5.59, XB1 4.77. We are not using zone 1 extension, zone 2 and zone 3 in this example. RCA is 70, minimum operating current is 0.5 and line impedance is 0.22 ohms per kilometer. Z minimum is 2 ohms, load forward angle 15, load reverse angle 15. These values are in line with the characteristics defined in railway standard. So you can see the XF, RF, RB and XB values reflected in the drawing as per the relay. And the load area plus or minus 15 is actually the load encroachment angle with Zmin as 2 ohms. So now let's incorporate the same thing in SMRT1 software. So this is the equivalent settings in SMRT1. So let's see how to incorporate these settings. Click on this advanced menu, click on the impedance tab. This will launch the impedance test panel. You can click on the library, click on generic and the quadrilateral characteristics. So you would be having the options to enter X, R, X, R, RCA and these values. So let's enter the values. Now we have entered all the values in line with the relay settings, and the load encroachment settings can be entered by clicking on this edit option. So 2 ohms and 15 degree. So once the values are entered, click on this tick mark. Click on this menu, the testing menu. So here you have 2 options. One is the short test and other is the reach test. The short test is used to do timing and the reach test is used to verify the boundary. So let's execute a short test and identify the results. So when I click on the short test, I get the characteristics along with load encroachment in line with the relay characteristics. Click on this, it will randomly select the points. If you wish to click more points, you can also do that. Then click on this play button. put a tick mark. Now you can see at each and every point that we have selected, it is injecting the respective current, voltage and impedance, and this is going to trip the relay and we will be getting the feedback. So if the test is within the timing and the reach, which are outside the zone, so there should not be any operation and hence it's pass. So this kind of table will be available in the results column.
So in this way, we have created the timing test, the characteristics, WPC. So let me show you the WPC test.
In this video, we are going to test wrong phase coupling, WPC. So let's see how to simulate this. We have to connect the feedback to the WPC contact. As per the specification, the WPC is an impedance test which is configured between 90 to 150 degree, that is in the second quadrant. So the distance protection is a quadrilateral characteristics in all the four quadrants, whereas WPC lies only in the second quadrant between 90 to 150. So in order to compensate the regenerative braking, this angle is kept as 150 degree. The impedance reach value also varies from 60 ohms at the upper limit and 2 ohms in the lower limit. So in RTMS software, let's use the standard distance protection module. So click here in the advanced menu. Click on the impedance option. So in the library, you can click on half circle. Here, click on this library, click on generic and click on this half circle option. In half circle option, you can select zone 1 on face to ground and you can enter the maximum reach as 60. This is in line with the relay settings. The angle, offset, all these are configured to ensure that the region lies in the second quadrant. Zone 2 is configured as 2 ohms. This is to ensure that you show the reach area between 2 ohms and 60 ohms. So any impedance inside this region will be under WPC. So let me put a tick mark. So this is the testing characteristics. So I have 3 options here: the short test, the linear search test, and the pulse search test. In short test, I can click on random points and verify the operation of the relay. In the second option, the linear reach test, we click on a point outside the zone and another point inside the zone. So what the test kit does is, it will inject an impedance outside the zone. Slowly it will reduce the impedance, waiting for the relay to operate, and at a particular impedance, the relay will operate. So this point is identified as the boundary. So this procedure is repeated in multiple points, and in this manner it will be able to identify the exact location of the boundary. This is little bit time consuming as it is going to start from the outer region and slowly navigate towards the inner region. So in places where you do not have sufficient time or you wanted to do the relay testing in an accelerated manner, we have the third option where we do a pulse search method. Here we have 2 points, one outside the zone and one inside the zone. So what the test kit does is it creates an impedance outside the zone. There should not be any operation. Another point inside the zone, there should be an operation. So if this is true, then it creates 2 more points which is nearer to the boundary. Let us say I create 1 point at 10 ohms and 1 point at 0. So the test kit will inject an impedance at 10 ohms, there is no operation, and at 0 there is an operation. So now assume that the boundary is 5 ohms. Now what the test kit does is it will move towards the boundary. So another point at 7.5 there is no operation, and another point at 2.5 there is operation. Then again it moves towards the boundary. So in this manner, by giving pulses at various points, it can easily identify the boundary. So let me do a short test. So this is the WPC region. I am going to click 1 point outside the zone. So there should not be a WPC operation. Randomly I am selecting 2 points inside the WPC region and 1 outside 150 degree. And 2 more points more than 60 ohms. So these are the points which I have selected. Only 2 points are inside, which is going to operate. So let me click on the play button. So the first point where there is operation on WPC, second point on WPC, the third point which is less than 90, so there is no operation, the fourth point more than 150, there is no operation, the fifth point outside 60 ohms, no operation, and the sixth point that's also outside 60 ohms, so no operation. So with this we can perfectly identify the region of operation. If we want to further identify the characteristics also, let me click on the quick search method. I can randomly click 1 point outside the zone and 1 inside the zone at multiple points. So let me run this. So it's injecting 1 point outside, 1 inside, and it is trying to identify when is the relay operating consecutively, and that point is identified as the boundary. So in this manner we can identify the exact boundary of WPC region in the same RX plane. So let's see the results by clicking here, saving impedance report. So it has 2 pages. Let's see page 1. This is the search test. You can see it has operated at 60 ohms, that is the outer boundary. And the next is the short test. So you can see it has operated at 34 milliseconds. So you can also see the region of operation, the region of non-operation along with the timing in a single test.
So in this way, you can just go through the video. Each video should be in the range of 10 minutes. So in 10 minutes, you can completely understand how to test a specific protection function. And you can test it by yourself because it's very, very simple. Already the theory part is completely available in the railway specification. And the configuration and how to take the values from the relay, how to enter the values in the testing software, all those things are explained in this video. So just by looking at it, you will be able to identify this.
You can download the RTMS software from this QR code and you can try all the features. Even if you don't have the test kit, you can try all the features which were described earlier. If you need additional support, you can use these QR codes to access the testing videos which are available online, where all the features such as distance differential, overcurrent earth fault, and even 61850 features has been demonstrated. Megger also provides relay testing services, where we do test kit rental as well as send our own engineers to site to test your relays. So for further information, you can contact us by accessing this QR code. To know more about the upcoming webinars, kindly scan this QR code. Let's wait for another 5 minutes. If you have any questions, please post it in the chat window. Our team will respond to it. Thank you.
Okay.